Hello, this is Mr. Mac. This is a video about independent events, dependent events, and conditional probability. Okay, now first of all, two events are independent if the fact that one occurs does not affect the probability that the other one occurred. So in other words, the probability of B is the same thing as the probability of B when we know A has occurred. This is written is read right here. The probability of B given A. In other words, what is the probability of B if we know A has occurred? Well, if the probability of B is equal to the probability of B given A, or in other words, if we know A occurred and the probability of B stays the same, then the two events are independent. Now, the formula for independent events, the probability of A intersect B when the events are independent is the probability of A times the probability of B. It's that simple. To get the probability that they both occurred, you multiply the probabilities that each occurred when the events are independent. Now, if the events are not independent, that isn't the case. Now, if events are dependent, that basically means they're not independent. In other words, if you know that event A occurred, then the probability of B is different than if you know it didn't occur, then the probability of one event depends upon the probability of the other event. Now, the formula for the intersection of A and B when they are not independent is the probability of A intersect B is equal to the probability of A times the probability of B after A occurs. Now, there's a little note here. When we are talking about what's the probability of this, that, or the other thing, a lot of times we use illustrations like we've got a bag of marbles or a bag of coins or something like this, and we take one out and then we take another out. And if we do not specify that we're replacing the object after each draw, then you have to assume that they are not replacing the object after each draw. So in other words, unless it says with replacement, we are not replacing the first thing that we draw when we before we draw out the second one. Now let's take a look at an example. A bag contains 4 red marbles and 3 green marbles. A marble is selected and replaced, and then another marble is selected. A, classify the event as independent or dependent. Well, since we put the marble back in, the probability of getting whatever we're going to get for the second drawing is exactly the same as the probability of the first draw because we have the same number of marbles of each type in the bag for that drawing. So the events would be independent if we replace that first marble before we draw the second one. Now it says construct a tree diagram of the outcomes. Okay, now we're going to select a marble. Okay, so we could select a red marble, or we could select a green marble. Now, usually on these tree diagrams, what we do is we write the probability that that has occurred right along the branch of the tree there. Now, since there are 4 red marbles, the probability here would be 4/7. And since there are 3 green marbles, the probability of this branch is 3/7. Now, we put the marble back in and we draw another one. So if we get a red the first time, we could get a red one on the second time, and that probability is 4/7 as well. Or we might get a green one on the second one, and that probability is 3/7 as well. Now, if we get a green marble on the first one, put it back in, the probability we get a red on the second draw is 4/7, and the probability we get a green on the second draw is 3/7. So this would be a probability tree. Now, notice this is the outcome red, red. This is the outcome red, then green. This is the outcome, green, then red. And this is the outcome, green and green. Okay, now to find the probabilities of each of these outcomes, what you do is you multiply the probabilities along the branches that get you to that leaf. In other words, the probability of red, red would be 4/7 times 4/7, or 16/49. Okay, now it says C, find the probability of red then green. Now if we go to the tree over here, red and then green is this leaf right here, and it would be 4/7 times 3/7. So the probability of red and then green would be 4/7 times 3/7, or 12/49. Now find the probability of red and red. Now the probability of red and red, let's use purple here, would be going here and then here. So the probability of red and red would be 4/7 times 4/7, or 16/49. Now find the probability that the two marbles are the same color. Now that would be red, red, or green, green. Now these don't overlap in any way. They're mutually exclusive events. So from an earlier video, we showed that this would be the probability of red, red plus the probability of green, green. And there would be no overlapping, so we would just say this would be 4/7 times 4/7 plus 3/7 times 3/7, which is 16/49 plus 9/49, which is 25/49. All right. Let's go on to example 2. A bag contains 12 quarters and 7 nickels. 2 coins are selected from the bag. Classify the event as independent or dependent. Actually, I think that would be classify the events as independent or dependent. Well, see, now we're going to select 2 coins from the bag. We're going to take one, and since we didn't say we're going to replace it, the second one is going to be taken after the first one is taken, but we're not replacing the first one. So these 2 events would be dependent. In other words, the number of coins of each type left in the bag would be dependent upon what we drew the first time. Now B, it says construct a tree diagram to represent the outcomes. Okay, well, let's see. We could have a quarter or a nickel. Now the probability of getting a quarter would be 12/19. And the probability of getting a nickel would be 7/19. Now after the first draw, we might get another quarter. Now, see, we did not put the first quarter back. There were 12 quarters. If we got a quarter out the first time, there's 11 quarters left. There's 18 coins left. So the probability of the second quarter would be 11/18. And we could get a nickel after getting the first quarter. Now there's still 7 nickels, but there's only 18 coins in there. So the probability of getting a nickel after drawing the first quarter would be 7/18. Now if we got a nickel on the first draw, we might get a quarter on the second draw. Now the probability of that would be 12, but there's only 18 coins, so 12/18. And we might get another nickel. If we got a nickel on the first draw, there would only be 6 nickels left. There would still be 18 coins, so the probability of a nickel on the second draw would be 6/18. Now it says find the probability of a quarter and a nickel. Now when we say quarter and a nickel, we mean the probability that we draw of the coins we drew, one's a quarter, one's a nickel. Now we have to think of both. In that particular case, we have to think of both the quarter and the nickel, that's this way, or the nickel, and then the quarter. So the probability of a quarter and a nickel is going to be 12/19 times 7/18 plus 7/19 times 12/18. Now, 7 times 12 is 84. 19 times 18, I don't know what that is. Hang on here. (19) times 18 is 342. So we get 342 on the bottom. Oh, what happened? We get 342 on the bottom, and we get 84 plus 84, which is 168 on the top. 168 over 342. And that does simplify to 28 over 57. So the answer to the probability of a quarter and a nickel is 28 over 57. Now I'm going to erase this here, so I know that if you need it, or if you want this explanation again, you can just roll the video back a little bit. There we go. Now, the next one says, find the probability of a nickel and a nickel. Now, there's only one way to get a nickel and a nickel. That's a nickel on the first draw, and then a nickel on the second draw. So let's get a highlighter here again, and we'll go with this one. That would be this path right here. So the probability of a nickel and a nickel would be 7/19 times 6/18. Now, 7 times 6 is 42. 19 times 18, I think we decided was 342. And 42 over 342 reduces to 7/57. So the probability of a nickel and a nickel is 7 over 57. Once again, you can roll this back if you want to see this again, or think about that some more, reducing that so we can get back to, okay, now, the last one, find the probability of at least 1/4. Now, the probability of at least 1/4 is the probability of quarter-quarter plus the probability of quarter-nickel plus the probability of nickel-quarter. Now, we could compute each one of those. In other words, quarter-quarter would be 12/19 times 11/18. Quarter-nickel would be 12/19 times 7/18. And nickel-quarter would be 7/19 times 12/18, and then I'll add all three of those together. Now, there is a little bit easier way to do this. And the easier way is to say that this is 3 of the 4 things that could happen. Now, all told, the probabilities of all the things that could happen would add up to 1. So we might just say this is equal to 1 minus the probability of nickel-nickel, which we just computed. So that would be 1 minus 7 over 57. And I think you know that 1 is 57/57. Minus 7/57 would be 50/57. So the probability we'll get at least 1/4 is 50 over 57. All right. Now, the next thing that we want to talk about is conditional probability. Conditional probability, I actually used it earlier. Probability of A given B. In other words, what we're saying here is what is the probability that A occurs if we know B has occurred? Now there's a formula for this. The probability of A given B is equal to the probability of A intersect B over the probability of B. See, in other words, if we know B has occurred, then the the set of all possibilities is the probability of B. And the probability that A happens is the probability that both A and B have occurred. So the probability of A intersect B over the probability of B is the probability of A given B. Now, also, let me just say here, if you take this formula and you multiply both sides by the probability of B, you get the probability of A intersect B is equal to the probability of B times the probability of A given B. And let me just say for a moment, if A and B are independent events, remember the probability of A given B is the same thing as the probability of A. And there is our formula for independent events. The probability of A intersect B is the probability of A times the probability of B. All right, let's continue on here. We have a utility company, and it's asked 50 of its customers whether they pay their bills online or by mail. What is the probability that a customer pays the bill online given that the customer is male? Okay, now the probability online given male is equal to the probability of online intersect male over the probability of male. Now we are going to use this chart right here. The probability of online intersect male is male person, not paying by mail, is 12 over a total of 36, no, 50, 12 over 50. So probability of online intersect male is 12/50. Now the probability of male is 20/50. And we can do a little math here. And what we get, here we go, is 12/50 times 50/20. And the 50s will cross cancel, and 4 will cross cancel in the 20s, so we get 3/5. So the probability the customer pays the bill online given the customer's mail is 3/5. Okay. Now, another example. A school system compiled the following information from a survey sent to people who were juniors 10 years earlier. 85% of the students graduated from high school. Of the students who graduated from high school, 90% are happy with their jobs. Of the students who did not graduate from high school, 60% are happy with their present jobs. And then we asked two questions. A, what is the probability that a person from the junior class 10 years ago graduated from high school and is happy with his or her present job? Given, and part B, given that a student is happy with his or her present job, find the probability that they did not graduate from high school. Okay, so one of the things that we can do here is we can do a tree diagram. This is going to help us some. Now we've got graduated, that's 0.85, and not graduated, that's 0.15. Now if they graduated, 90% are happy, 0.9, and 0.1 are unhappy, or maybe I should just do not happy. Not happy. Now, if they didn't graduate from high school, 60%, 0.6 are happy, and 40% then are not happy. All right, so what is the probability that a person from the junior class 10 years ago graduated from high school and is happy with his or her present job? That would be moving along this path right here. Graduated and is happy. I don't know why it straightened that out. I wanted that to be curved. There we go. So we would say that's 0.85. times 0.9, and that would be 0.765. So we would say that 0.765, or 76.5% of the time, we would expect the person graduated from high school and is happy with their job. Now, part B says, given that a student is happy with his or her present job, find the probability that they did not graduate. Now, happy with their present job is actually these, this spot and this spot. So the 0.765 that we have plus 0.15 times 0.6, which is 0.09, I think. 0.15 times 0.6, 0.09. So not graduate and happy is 0.15 times 0.6, which is 0.09. I'll just put 0.09 right here. This is 0.765 there. Now, so the conditional probability, what is the probability that, what is the probability that they did, given the student is happy, what is the probability that it did not graduate from high school? Well, the probability happy given not graduate is equal to the probability of happy intersect not graduate over the probability of happy. Ooh, no, I did that wrong here. Hang on just a second. Let me go back and do this again because they've stated this in the opposite way. All right. Given that a student is happy, find the probability that did not graduate. So what is the probability they did not graduate given they're happy? See, that's what they gave us. They gave us that they were happy. So that's equal to the probability of the intersection of not graduate and happy over the probability of happy. Okay, now the probability of not graduate and happy is 0.09, and the probability of happy is 0.765 plus 0.09. See, those two leaves both say they're happy, and they're either they graduated and are happy, or they didn't graduate and they're happy, and so we add those up. And what do we end up getting on this one? Let's see, 0.765 plus 0.09. I get 0.09 over 0.855. Now, we probably need to clean that up some. So if we ask the calculator, it will tell us that the equivalent fraction is 171 over 200. So the probability that a student didn't graduate high school, given that they're happy, is 171 over 200. No. 0.09. Oops. Over 0.855. Oh, excuse me. This isn't right. I didn't do the 0.09 divided by 0.855. I just did the 0.855. So what do we got here? We've got this turns out to be the decimal 0.105263157, etc. Now, I don't know if the calculator is going to be able to tell me what that is as a fraction. Oh, yes, it is. This turns out to be 2/19. Wow, okay. So that's the answer to B. All right. Um, let's move on. The next concept is, how do you prove independence? Well, basically, since the probability of A times the probability of B is equal to the probability of A intersect B when the events are independent, that's what we do. We multiply the probability of each event occurring, and if we get the intersection, the probability of the intersection of the two, then we say the events are independent. If we don't, then the events are not independent. Okay, so example 5, each student in a class of 30 students, each student in a class of 30 studies one foreign language and one science. The students' choices are in the table below. Find the probability that a randomly chosen student studies chemistry. Well, this is the total of the students that are studying chemistry. This is the total of students all told. So we would say the probability of the randomly chosen student studies chemistry is 8 over 30, which reduces to 4/15. Second question. Find the probability that a randomly chosen student studies chemistry given that the student studies French. Okay, so we know that the student is studying French. There's 14 of those. And we want the probability that the student studies chemistry given that they study French, and that would be 7. So we have for B, 7 over 14, which reduces to 1/2. Now, are the events student studies chemistry and student studies French independent? Student studies French and student studies chemistry is 7/30. 7 over 30. Student studies French. Okay, student, which this a little smaller. Okay, I'm just going to go down here. You're going to have to look at your page or go back up. So, student studies chemistry. Probability that student studies chemistry is equal to 8/30 or 4/15. The probability the student studies French is 14/30, which reduces to 7/15. Now, the probability that a student studies chemistry and French is equal to 7 over 30. And so is 7 over 30 equal to 4/15 times 7/15? Well, no, it isn't. So the events are not independent. So we would say a resounding no on this one. And that concludes the talk for conditional probability and the examples. So we're done.